Welcome to our advanced DSA series. Today, we're exploring greedy algorithms, a powerful technique used to solve optimization problems efficiently. Whether you're tackling coding interviews or competitive programming challenges, understanding greedy algorithms is essential. Greedy algorithms are a problem-solving technique that works by making the best possible choice at each step, hoping to find the overall optimal solution. The idea is to choose the option that seems best at the moment without worrying about the future consequences. For a greedy algorithm to work, two main conditions must be met. Firstly, the greedy choice property, and then the optimal substructure. A classic example of greedy algorithm is the activities selection problem. Given a set of activities with start and end times, the goal is to select the maximum number of activities that don't overlap. In this activity selection problem, first, we sort the activities by their finish time. We then select the first activity and continue to select the next activity that starts after the current activity finishes. Unlike dynamic programming, where we consider all possible solutions and choose the best one, greedy algorithms make decisions based on the current situation without revisiting or reconsidering previous decisions. This makes them faster, but they only work when the problem has the greedy choice property and optimal substructure. Greedy algorithms are used in various real-world applications such as Huffman coding, Dijkstra's algorithm, Prim's algorithm, fractional knapsack problem. Let's look at Huffman coding. Huffman coding is a lossless data compression algorithm. It assigns variable length codes to input characters, with shorter codes assigned to more frequent characters. Now, let's look at the steps followed for Huffman coding. First, build a priority queue.
Second,
Build the Huffman tree. Lastly, generate codes. In this code, the node structure defines a tree node with a character, its frequency, and pointers to left and right children. Comparison function. This function tells the priority queue to sort nodes based on their frequency in ascending order min-heap. Then comes the process of building the min-heap. All characters are inserted into the priority queue with their corresponding frequencies. The two nodes with the smallest frequencies are combined to form a new node, which is then pushed back into the queue. This process continues until there is only one node left, which represents the root of the Huffman tree. The remaining node in the min-heap is the root of the Huffman tree. The printcodes function recursively traverses the Huffman tree. It generates binary codes by appending 0 when going left and 1 when going right. Dijkstra's algorithm finds the shortest path from a source node to all other nodes in a weighted graph with non-negative weights. Steps involved are initialize distances, priority queue,
and
relax edges. In this C++ code, we use pairs to store the vertex and the distance from the source. This helps in the priority queue, where we prioritize based on the shortest distance. This min-heap priority queue helps select the next vertex with the shortest known distance. Distance vector keeps track of the shortest distance from the source to each vertex, initialized to infinity except for the source vertex. Start from the source vertex with a distance of 0 to initialize the source. Extract the vertex with the smallest distance, u, from the priority queue. For each neighbor v of u, check if the path through u offers a shorter distance to v. If a shorter path is found, update the distance and push the updated distance into the priority queue. Prim's algorithm finds the minimum spanning tree, MST, for a graph, which is a subset of the edges that connect all vertices with the minimum total edge weight. Steps for Prim's algorithm are initialize, select edge,
and
update queue. In this code, key vector stores the minimum weight edge connecting a vertex to the MST, initialized to infinity. Parent vector tracks the parent of each vertex in the MST. In MST, Boolean vector to track if a vertex is included in the MST. Start from the first vertex with a key value of 0. Extract the vertex U with the smallest key value and mark it as included in the MST. For each neighbor V, if V is not in the MST and the edge weight to V is smaller than its current key, update V's key, push it into the priority queue, and set its parent
to U.
Output the edges that form the MST. Fractional knapsack problem is an optimization problem where you can take fractional amounts of items to maximize the total value in a knapsack of limited capacity. Steps involved are: calculate ratios, sort items,
and
fill knapsack. In this C++ code, the item structure represents an item with a value and weight. Comparison function sorts items by their value-to-weight ratio in descending order. Sort the items based on their value-to-weight ratio. Start adding items to the knapsack based on the sorted order. If the full weight of the next item fits, take it all. If not, take the fraction that fits. Display the maximum value achievable within the given knapsack capacity. To sum up, greedy algorithms are a powerful tool for solving optimization problems efficiently. They make locally optimal choices with the hope of finding the globally optimal solution. Remember, they work best when the problem exhibits the greedy choice property and optimal substructure. That's all for greedy algorithms. If you found this video helpful, be sure to like, share, and subscribe for more in-depth DSA content. Got questions or suggestions? Drop them in the comments below, and let's keep learning together.